Mentioned the word conjugate in the last video, and we used that word when we were dealing with complex numbers, and for us it came up in a division problem, complex numbers with division. A conjugate is really useful in a division problem with complex numbers because we can get the imaginary part of a number out of the denominator. We can get it out of there, and if you want to see that, you can look at our complex video introduction. But here I want to talk a little bit about what the conjugate is, because I mentioned it but it didn't really define it. So we can write conjugates as z with the line over it, and that line's called a vinculum. But if you see a z with a line over it, that means you're writing the conjugate of a complex number. So if we have a number, a plus bi, so this is a complex number, right? We have a, which is some real part. That's the real part of the number. It could be 1 or 2 or 3 or any rational number. So that's our real part. Excuse me, not only rational but also real, so it could be irrational numbers as well. But over here we have our imaginary part. So that's together with the imaginary and the real, we have a complex number. Well, the conjugate is always going to be the same thing. We have the exact same value for the reals, but the opposite value for the imaginary. So that's what a conjugate's all about. If we have a complex number, we take its conjugate by keeping the real number the same, but switching the value of the imaginary part to its opposite. So positive bi becomes negative bi. And let's just look what happens when we take something, let's say z, and multiply it by its conjugate. So z times its conjugate. What's going to happen? Why is this useful? Well, if z is a plus bi, and the conjugate is a minus bi, if we multiply these two, we use the distributive property. A times a is a squared. A times bi is, a times minus bi is minus abi. Bi times a, you can think of that as positive abi. And then, well, again, what I did there was bi times a. I changed the order that I was multiplying in, so these two terms will look identical and be easy to recognize. We can do that because of the commutative property of multiplication. Anyway, in the last step we have positive bi times negative bi, so it's negative b squared I squared. So let's just look at why this is really awesome. When we do this, we keep a squared. There it is, all alone, a squared. But we're always going to get, it doesn't matter what this is a general equation, right? It doesn't matter what we start with. As long as it's the conjugates, we're going to get a negative bi and a positive bi. Those are opposites, that adds to 0. And then minus b squared times I squared. Well, we don't know what b squared is, but we do know that I squared equals the square root of negative 1 times the square root of negative 1. And that's just negative 1. So we have a squared, I don't need that 0 there anymore, minus b squared times negative 1, which is a squared. B squared times negative 1 is negative b squared. So it's a squared minus a minus b squared. An easier way of writing that is a squared plus b squared. So when we multiply by our conjugate, we have our original number a plus bi. If we multiply by the conjugate, we're just going to get a squared plus b squared. It's a nice shortcut. And you might actually be able to memorize that, but I prefer to set this up and think it through each time, because math is set up in a way so you don't have to memorize, but can think your way through it. And here all we had to really use was the idea of the distributive property to see what would happen. That's the idea of the conjugate.